Hi class, welcome back to multivariate calculus. In this lecture, we are going to practice computing line integrals. So remember from last time that if the position vector, so the position vector is r of t for some time interval from a to b along t, and these should be less than or equal to signs. If the vector is a smooth parameterization of some oriented curve C and some vector field F, which is continuous on C, then the line integral of f dot dr is equal to the integral from time A to time B of f as a function of time using our parameterization for r, dotted with the first derivative of our position, dt. And this is just a review from last time. So let us go ahead and compute the line integral. Feel free to try this on your own first too, but we're going to compute the line integral for the vector field f is going to be x times y I hat plus x j hat along the parabola y equals x squared from position 1, 1 to 2, 4. Okay, so now first we have to come up with a parameterization for y equals x squared. So r of t, all right, so for our parameterization, remember each component has to be a function of time. And so we want to start at position x equals 1, y equals 1, and end at position 2, x equals 2, and y equals 4. So for our x component, let's call that t. And so remember, y is equal to x squared. So if x is equal to t, then y is equal to t squared. And now we need our time interval. So to start at 1, 1, t has to equal 1. So when t is 1, we have 1 I hat plus 1 j hat. And then we're going to go to 2 because then we'd have 2 I hat plus 2 squared j hat, so it would be 2, 4. All right. So then let's take the first derivative of our position vector, and that is going to be I hat plus 2t j hat. And so then we're going to plug it into our definition up there. So f dot dr, the integral, the line integral, is equal to then going from time 1 to time 2 of, then we have our f, which is xy. And so x is going to be t, and y is going to be t squared. So it's going to be t cubed I hat. Actually, I'll write this out so you can see it. So f of r is going to be t cubed I hat plus we have x j hat, and x is just t. Okay, so let's plug that in first. And then we're going to dot that with r prime t. So that's going to be I hat plus 2tj hat dt. So the dot product then is going to be, we have the integral from 1 to 2 of t cubed times 1, which is just going to be t cubed, plus t plus 2t, which is going to be 2t squared. All right. And so then if we integrate, that's going to be t to the 4th over 4 plus 2t cubed over 3, evaluated from 1 to 2. All right, so it's going to be 2 to the 4th over 4, which is going to be 4, plus 2 cubed times 2 over 3, which is going to be 16 over 3, minus 1 over 4, plus 2 over 3. And so if we simplify, let's take 12 as a common denominator. We have 48 plus 64 minus 3 minus 8. So this is going to be 101 over 12. Okay, so that is it with that. And now we're going to do another one. And I would like you to try this one on your own once I actually give you the rest of the information for this problem here. So we're going to compute the line integral for the vector field f is going to be x, y, I hat plus x, j hat. And we're going to go along the straight line from 1, 1 to 2, 4. Okay, so think about what type of parameterization you will need for this to get the position vector. So try this on your own, give it a pause, and proceed when you're ready to see the solution. So our position vector, r of t, there are several different parameterizations you can come up with. This isn't the only answer. So one such would be if we have 1 plus t I hat plus 1 plus 3t j hat for 0 is less than or equal to t is less than or equal to 1. So let's just confirm here. So when at a time of 0, we want 1, 1. So at a time, so we have to have 1 plus our time for each is one way we can do this. So this gives us an initial position of 1, 1. And then if we plug in 1, well, 1 plus 1 is 2. And then in order to get to 4, you have to have 3t. Because remember, this is a straight line here. Okay, so for a straight line, the form of a straight line is y equals mx plus b. So some intercept, some slope, and the slope times our variable, which is time. Okay, so that's the form of a straight line. Okay, so then we take the derivative. R prime of t is going to be I hat plus 3j hat. And then f as a function of r is going to be, well, this gets a little bit messy. So for x, we have to plug in 1 plus t. For y, we have to plug in 1 plus 3t, and that's our I hat. And our j hat is going to be 1 plus t j hat. So let's just expand, or distribute. We have 1 plus 4t plus 3t squared I hat. And then we have our 1 plus t j hat. Okay, so then plugging into our definition, so work, or our line integral, is going to be on the interval from 0 to 1 is what we determined. So you plug in what you determined for the time interval here for the limits of this integral. And we're going to go from, and then we're going to do our dot product. And so we have 1 plus 4t plus 3t squared I hat plus 1 plus t j hat dotted with I hat plus 3j hat dt. And so this is going to give us the integral from 0 to 1. And then we have our I hat component is going to be 1 plus 4t plus 3t squared. Then add on our j hat component, which is going to be 3 plus 3t dt. Now let's add all these together. Simplify. And we get 4 plus 7t plus 3t squared dt. Okay, so let's integrate. So we end up with 4t plus 7t squared over 2 plus t cubed. And we're going from 0 to 1. And you get 8 plus 7 plus 2 over 2, which is 17 over 2. Now, you could have selected a different parameterization with a different time interval, and how you can check to see if it works is you should still get the same result. You should still get 17 over 2. So if you did not get that, then there was something amiss with your parameterization. And just remember, traveling along a parabola is going to be a different distance than traveling along a straight line, right? So that's why basically here we did the same thing, except we traveled along a different path. Okay, let's try another one. We're just going to keep on practicing these today. So we're going to find the work done by the vector field F is going to be 2x I hat plus 3y j hat plus z k hat. Okay, so we're in 3 space now. In moving a particle along the circular helix, given by r of t is equal to cosine t I hat plus sine t j hat plus t k hat from t equal to 0 to t equals to pi. So now let's start with r of t. Okay, which is given to us. Just going to rewrite it. Okay, cosine t I hat plus sine t j hat plus t k hat. So this is producing a helix here. And our first derivative then is going to be minus sine t I hat plus cosine t j hat plus k hat. And if we plug in our components into our vector field, so if we write our vector field as a function of position, And I've just started leaving out the t here. It's implied. But if you feel more comfortable writing r of t, feel free to do so, is equal to 2 cosine t I hat. Okay, since it's going to be 2x, and our x is cosine t, plus 3 times sine t, which is our y, plus z k hat, and our z k hat is just t k hat. Okay, and so remember our definition, work is equal to the line integral of f dot dr, as we've been doing. So this was just a slightly different way of asking the same question that we've been working with today in today's lecture. And so then we're going to get the integral from 0 to pi, since that's our time interval, of 2 cosine t I hat plus 3 sine t j hat plus t k hat dotted with r prime t, which is minus sine t I hat plus cosine t j hat plus k hat dt. My double parentheses here are a little messy. Let me just fix these. One, two. Okay. And so let's take the dot product. And we have minus 2 sine t cosine t plus 3 sine t cosine t plus t dt. All right. And so let's actually split up this interval just a little bit. And I'm going to add a sheet since I'm running out of room. Okay. So we can rewrite this as equal to the integral from 0 to pi of, so now notice that what we have is we have minus 2 sine t cosine t plus 3 sine t cosine t. So that's just going to be sine t cosine t. Plus t dt. And we can actually split up these intervals so it's a little easier to evaluate. So this is going to be equal to the integral from 0 to pi of sine t cosine t dt plus the integral from 0 to pi of t dt. So let's just start by evaluating t dt, since that is going to be pretty easy. Actually, I'll leave that alone for now. Let's just focus on this one first. And we're going to do a u sub. So we're going to let u equal sine t. So du is going to equal cosine t dt, which means that dt is equal to du over cosine t. So that means we have the integral of cosine t times u du over cosine t, which is just going to be u du. So then we end, which is going to be u squared over 2 once we integrate it. So we end up with u squared over 2 is going to give us sine squared t over 2. Plus, then we want to integrate this piece right here, and that's going to give us t squared over 2. And we're going to go from 0 to pi, which is going to give us 0 plus pi squared over 2, which is just going to be pi squared over 2. Okay, so that's it with that one. And we're going to do another problem, and feel free, of course, once I give you the rest of the problem, to try it out on your own first. That is definitely encouraged. So we're going to find the line integral of x minus y dx plus x y dy, where our curve C is the line segment from 0, 1 to 2 minus 1. All right, so feel free to try it on your own first, but I'm going to continue now. So now what we're seeing here is this is going to be our field, our vector field as a function of space. So that's telling us that f is equal to x minus y I hat plus x, y, j hat. Okay, so that's our field component, because remember, it's also, we can also take the form of f dot dr, where r and f are both functions of space rather than time. So that's what we're looking at here. And so then we know that dr then, because this inside this integral here is f dot dr, is what's given to us. So dr as a function of space is going to be dx I hat plus dy j hat. Okay, so we know that f dot dr is all of this, right? X minus y dx plus x, y, dy. All right, so now we have to come up with some parameterization of our position vector. So let's see, we need a line segment that goes from 0, 1 to 2 minus 1. So let's say that r of t is going to be 2t I hat plus 1 minus 2t j hat, going from 0 to 1. And I like to choose the time interval 0 to 1 just because it's really easy to work with, but you can do whatever you would like. Because remember, we're going from, for the x, 2 minus 0, we're going 2. And for the y, we're going minus 1, minus 1. So we're going minus 2. And so starting at t equals 0, we have 0, 1. And ending at time 1, we have made this be 2 times 1 is 2, and 1, excuse me, and 1 minus 2 is minus 1, so that works. And then we can take our first derivative, which is just going to be 2i hat minus 2j hat. All right, and so now let's rewrite f as a function of time, as a function of r of t. And so this is going to give us 2t minus 1 plus 2t I hat plus 2t times 1 minus 2t j hat. So just plugging our x equals 2t in for x, and our y equals 1 minus 2t in for y is all we did there. And so we could simplify this a little bit, and we end up with 4t minus 1 I hat plus 2t minus 4t squared j hat. So the line integral of f dot dr is going to be for us on the interval of 0 to 1. And another reason that it's really nice to use the time interval a lot of times from 0 to 1 or from 0 to some number is that when you evaluate the integral, you only have to plug in the upper limit for most cases, right? Because typically when you plug in 0 for a variable, that will become 0. Typically, not always, right? Not especially if you're using trig functions. But just a little pointer. So we're going to do 4t minus 1 I hat plus 2t minus 4t squared j hat. And we're going to dot that with 2i hat minus 2j hat dt, which is going to give us the integral from 0 to 1 of 4t minus 2 plus 4t minus 8t squared dt. Oh, 8t. Just kidding. 8t minus 2 plus 4t minus 8t squared. Now I'm going to keep going on a new sheet. Whoa. Just zoom out a little. What happened? Okay. So, keep going. We're going to have the integral from 0 to 1 of 8t squared plus 4t minus 2 dt. And this is pretty straightforward from this point to integrate. And so we end up with 8t cubed over 3 plus 2t squared minus 2t from 0 to 1. And so we just end up with 8/3 plus 2 minus 2 minus 0, which is 8/3. And that is it there. So kind of fun, right? Now, I have one more for you to go through. And this is really kind of like a bonus problem. I'd like you to try this on your own. Try to challenge yourself. Really think it through before watching my solution. A 160-pound man carries a 25-pound can of paint up a helical staircase that encircles a silo. So here's our silo with a radius of 20 feet. If the silo is 90 feet high, so that's our height here, 90 feet, and the man makes exactly 3 complete revolutions around, how much work is done by the man against gravity and climbing on top? So really climbing to the top. Really try to think this out physically. So pause it, try it on your own. Okay, welcome back. Now, what we need to do, or one thing, is that let's think about what is going on here? Let's think about the physics of this a little bit, and it looks like I have an intruder, so just give me a sec. This guy and a little intruder. Oh, happy kitty. All right, I'm gonna stop doing that. All right, now that she's not, well, now she's on my lap, which is gonna make it pretty challenging. Okay, let's try this. Where was I? Sorry for the distraction. All right, so let's think about mass for a second. So we have an 165 man carrying 25 pounds of paint. So what we want to think about is what's happening, right? So what force is acting against the man? Well, it's going to be the acceleration due to gravity. So he's going to have to overcome that to climb upward. So let's start with the mass. Remember that the force of gravity is equal to mass times the acceleration due to gravity, right? And that's going to be acting in, so that's going to be acting in the minus k hat direction if we're thinking about this in 3 dimensions, right? And so this 90 feet is our z component because we're going around basically the unit circle as far as the xy plane is concerned. So let's think about our mass. Our mass total is going to be 160 pound man plus the 25 pounds of paint. Okay, so it's going to be 185 pounds. And English units are really kind of messy, but not messy. Like the pound mass is this sort of mysterious thing where we typically think about it as the pound force on Earth. And so that already encompasses the acceleration due to gravity, which is, I think, 62.4 feet per second on in English units. So in this case, our force is just going to be minus 185 pounds in the k hat direction because that encompasses gravity in there. So that's our pound force that we're overcoming. We know our radius is, so this isn't the position vector, this is the radius, is 20 feet. And actually what I can do to make it a little less confusing, capital R for radius. So our parameterization for position, remember we're going around and around and around in a helix. So we did a helix example earlier this lecture. So our parameterization is going to be our radius cosine t, for example, in the I hat direction. So this isn't the only answer here, but just make sure your time interval works out. Plus 20 sine t for the j hat component. Now, this is actually the part that is the trickiest. So we're going to complete 3 full revolutions, and 1 revolution is 2 pi around a circle. And so we want to complete 6 pi in 90 feet. So we need 30 feet per revolution. So 30 feet of height per revolution since we're going around 3 times. And so that means it's going to be 30 over 2 pi, which is going to be 15 over pi for each revolution around. Okay, so our K is going to be 15 t over pi k hat upward. And then our time interval is going to be 0 is less than or equal to t is less than or equal to 6 pi, since we want 3 full revolutions. So then our derivative is going to be minus 20 sine t I hat plus 20 cosine t j hat plus 15 over pi k hat. All right, so now let's set up our integral. So we are going to go from 0 to 6 pi, and f is minus 185. And notice this is our k hat component. So really these I hats and j hats don't matter so much because we don't have any x and y components in our force field here. And so when you do the dot product, 0 dotted with 20 sine t is minus 20 sine t is going to be 0, and 0 dotted with 20 cosine t is going to be 0. So jumping ahead, we're left with minus 185 times 15 over pi dt, which is going to give us minus 2775 t over pi, evaluated from 0 to 6 pi, which is going to be 16,650. And our units here were pounds and feet, so it's going to be foot-pounds is the amount of work it's going to take. Force times distance. All right, so that is it for today. And we only have a few lectures left this semester. So next time we'll be getting into path dependence, and we're going to finish the semester up with Green's theorem. So take care, and I'll see you then.